Pleased to introduce Giulia Sacca, one of our own here at the moment, who's going to talk about compact Hyperkähler manifolds in algebraic geometry. Before she starts, I should say there's going to be a dinner afterwards, and if you want to be part of that dinner, then you have to contact Draw over there.
Just tell me after the lecture.
All right. Well, first of all, I'd like to thank your organizers for inviting me to speak here. I'm really honored to be here. So I will start by just giving an overview of my field of research, and then I will focus on two main results that I have improved with some collaborators. So let me start with a general introduction. So in algebraic geometry, one of the basic problems is to classify algebraic varieties. And one way to do it is to look at the first-string class of their the tangent bundle, their holomorphic tangent bundle. And using properties of this first-string class, you can find sort of coarse classifications of algebraic varieties. For example, for the cases of Riemann surfaces, there are only three cases. Either the first-string class, so if I have a Riemann surface sigma, the first-string class of sigma is negative, or it's 0, or it's positive. So in this case, the only Riemann surface we have is P1. In this case, we have elliptic curves, and in this case, we have higher genus curves. Genus greater or equal to 2. In higher dimension, there are a lot more cases than these. So not every algebraic variety has a first-string class which is definite or 0, either positive or negative or 0. But still, it makes sense to talk about algebraic varieties that have this property. So in higher dimension,
You mean because it's in a vector space of more than one dimension?
sorry?
Because it's in a vector space of more than one dimension, so you can't talk about its sign? Is that what you mean?
Well, sometimes you can, but not necessarily. Yes. Yes.
Okay.
Yes, absolutely. Yeah. Yeah. And also, of course, you can take products. So that would. Yeah. So in higher dimensions, you can still. Sometimes this happens, and this is called the varieties that fall in this class are called Fanos. These are called. Well, some people call them Calabi-Yau. I will say another definition of Calabi-Yau later. And these are called general type.
So pursuant to what Dennis was asking, the point is that, so on a Riemann surface, C1 is a number. There's,
Right.
there's an associated partial ordering in higher dimensions.
Right, and I mean, just take the product of something like this and something like that, and it's not definite anymore. And of course, yeah.
What is the analog of this number being negative, 0 or positive? What is the condition?
Well, that the first-string class is represented by a positive or negative class. So this means this means that the corresponding line bundle. So if you take the tangent bundle, you can take its top determinant, and this is a line bundle, and you can ask if the sections of this line bundle or the section of the powers of this line bundle separate points. Or equivalently, you can say that if there's embedding in projective space, such that the restriction of O of 1 from projective space, or O of some powers, restriction of O of 1 is this thing to the power 1 or negative 1. But in general, as I said, you can take products of things that are positive with things that are negative, and so that yields examples that don't fall into these three categories.
So positive means there's a lot of sections?
Yeah, positives means that up to taking powers of this line bundles, there are a lot of sections. And there are sections that if you take any 2 points on your variety, that you find a section that vanishes on one and not on the other. And this allows you to use the sections to embed in projective space.
It also stated in terms of whether C1 can be represented by a Kähler class or by a minus a Kähler.
But exactly, yeah. So what I'll be talking about today is the case where C1 is equal to 0. So let me give a definition. And compact Kähler is called holomorphic symplectic if it is simply connected and if there exists a holomorphic symplectic form. So holomorphic here means that locally, in a set of complex coordinates, I can write it as a holomorphic functions times dzi wedge dzj. And the symplectic form is a non-degeneracy condition. So it just means that, so this, at every point, this is a symplectic form on the holomorphic tangent bundle. So in particular, it means that the complex dimension of M is equal to 2n. It's even. So the condition of being symplectic is equivalent to considering the wedge product of this form with itself and times, this is just a determinant point by point of the symplectic matrix, and to ask that it's nowhere 0. In fact, this is a holomorphic form of top degree. And this implies that this, I forgot, didn't have it. Okay, that the top wedge power of the cotangent bundle of M is trivial. In particular, its first term class is trivial. So this class of varieties fall into this category. Let me give an example before I talk about the role of these kind of compact Kähler manifolds in algebraic geometry. So, so before I give an example of the compact Kähler manifold with this property, let me just remark that C2n has a natural symplectic form, just given by sum of dzi wedge dzj. These are holomorphic coordinates on C2n. And also the cotangent bundle, just like in the case of standard symplectic manifolds, the holomorphic cotangent bundle of any.
So I think you want to say J is.
Yes, sorry,
like
of course, yes, of course. Thank you.
Something I guess from one to n.
Yeah. And a holomorphic, that's another example. I should notice here that, well, this is automatically closed, and so is the one that you naturally construct here. Here I didn't ask for the symplectic form to be closed because this is automatically true if M is compact Kähler. But in general, that's when you define a symplectic manifold, you need this condition. So let me give an example of a surface, of a compact Kähler surface that is holomorphic symplectic. So let me consider a torus of dimension 2, C2n modulo a lattice of rank 4. This clearly has a holomorphic form that comes from the one on C2. And let me consider the quotient. Let me call this T. I can take the quotient by plus or minus 1. So this involution here has 16 singular points, fixed points, so there are 16 singular points here. And the local structure of these singular points is a very sort of well-known case. It looks like this, something like this, like a cone. And there's a natural resolution, which looks something like this, which can be described as a cotangent bundle of P1. And here I'm contracting the 0 section. So because this has a holomorphic symplectic form, I can glue all the symplectic forms coming from these local resolutions, and this gives me a global resolution. So this is a compact Kähler surface with, which turns out to be simply connected, which has a holomorphic symplectic form. This is called a Kummer K3. So these holomorphic symplectic manifolds arise very naturally in many fields of math, in physics and representation theory, and also in differential geometry and in algebraic geometry. So I'm an algebraic geometer, so that's the kind of holomorphic symplectic manifold that I study come in algebraic geometry. But the interesting thing is that the role of these things in algebraic geometry, in fact, so to see, it's differential geometry that has given a particular role to this class of manifolds in algebraic geometry. So let me mention the decomposition theorem. So I should attribute it to Pavel Bogomolov. But I should, well, later I'll say that it relies on a work of Dram and Berger. So what is the statement of this theorem? So this is it's a structure theorem for varieties with C1 equals to 0. So the statement is that if M is compact Kähler with C1 equal to 0, then there exists a finite cover finite unramified cover, which breaks into a product of some so-called irreducible factors. So I have the tori, I have the so-called strict Calabi-Yau.
You're assuming it's complex symplectic?
No.
Only C1 equals to 0. What I'm saying is that compact symplectic arise naturally as building blocks for varieties with this form, and because of this theorem. So the factors, the irreducible factors, the building blocks of these varieties are the tori, these strict Calabi-Yaus that I'm going to define in a second, and these symplectic manifolds, except that here I'm adding the word irreducible. Holomorphic symplectic. And from now on, I'll denote these by IHS.
So then you might have several factors of these irreducible.
Yes. So yeah, that's why I had an S. Tori, yeah, absolutely. And so these are simply connected and don't have any holomorphic form except in top degree. And these are, so what are these? These are holomorphic symplectic manifolds. These are holomorphic symplectic manifolds with the extra condition, so in the definition there, with the extra condition that the symplectic form is unique up to scalar. And so the irreducibility here, you can think of it both as saying that it doesn't decompose further, but also in terms of the holonomy group. In fact, I mean, behind this theorem, there's a work of Durand and Berger classification of holonomy groups, and also Yau's solution to the Calabi-Yau conjecture. And in fact, there's a sort of a holonomy interpretation for these factors. Here I have holonomy equal to SPR. So in fact, the irreducible here, I should add also an irreducible here, but it means that the holonomy representation is irreducible. These are SUM, and these are flat. Let me remark that thanks to this theorem, holomorphic symplectic is equivalent of existence to the existence of a so-called Hyperkähler metric. And what this means is that I have a Kähler metric that is Kähler not only for one complex structure, but there's a whole sphere, a P1 of complex structures. And this gives rise to something called the Krister family, which, though it's a very intrinsically non-algebraic object, in fact, the total space of this Krister family is not even a Kähler manifold, but they're actually used in proving theorems in algebraic geometry. And so I don't think I will focus on this aspect, but it's something that these twistor lines actually are in the back of some of the things I'll say.
Maybe it would help if for the definition of strict Calabi-Yau, m has to be greater than or equal to 3. Because otherwise you have SU2.
Absolutely. So for the case of n equals to 2, well, you can, the two conditions are the same, and so you can decide if you want to put one in one or the other. So this corresponds to the fact that a K3 surface, which is a simply connected Kähler surface with a unique up to scalar holomorphic symplectic form, is both a Calabi-Yau in this sense and a Hyperkähler manifold, or a reducible holomorphic symplectic. And from the point of view of this just tells you that, if you put the right number here, maybe 1 and...
Maybe it's better to move it to the other side since, for example...
yeah, I want to move them
Like
here.
the strict Calabi-Yau,
Yeah,
for example, we projected. Right? So.
Yes. Absolutely. Yeah. 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 And in fact, these holomorphic symplectic manifolds are the true generalization of K3 surfaces. And something that I'll hope to show in the talk is that a lot of the properties that hold for K3 surfaces actually hold with these higher dimensional irreducible holomorphic symplectic manifolds, which is something...
Did you say what irreducible meant? I forgot.
Irreducible means that the holomorphic form is unique up to scalar. So it's just one of the factors. You can't decompose it further.
It is the same as
also as holonomial irreducible. Exactly. So the problem is that there are very few examples known.
Actually, in the remark, is irreducible holomorphic symplectic which are equivalent to the system of Hyperkähler metrics or just holomorphic?
No, because you can take product of Hyperkähler things and that would be Hyperkähler. So the problem is that up to deformation there are very few examples. And
for the kindergarten people like us, so these are like generalizations of the torus. To say it's a generalization of K3 is too hard for me. So. I mean, they're very special somehow, first of all, right?
yes, they're very special.
The torus is very special.
But this example here was the one she wanted you to think about, I think.
No, I know.
So
People who aren't.
So yes, they're very special, but at the same time, I think they appear very naturally.
Yeah.
And the non-compact examples appear very naturally. It is true that the compact examples appear a little less naturally, but in fact, they're one of the building blocks, so it's something that you want to study. I mean, the strict Calabi-Yaus are studied by the physicists and string theorists, and there are tens of thousands of examples, even only in dimension 3. So if you want another thing to hold on about like a K3, you can think of, I don't know if this helps, but this, if you take the Fermat quartic, or even if you take a homogeneous polynomial of degree 4 in P3, so in four homogeneous variables, and so if this is general enough, that's going to be smooth. And in fact, that's a K3 surface. So maybe that's sort of another way of... in fact, all K3 surfaces are deformation equivalent. And they're all diffeomorphic. That was an old theorem of Kodaira. They're all Kähler, thanks to work of Siu. And so this moduli space is connected. And so this, and this are just two different projective realizations. This is not always projective. Two different geometric realizations of this class. So let me talk about the examples in dimension higher. And for every 2n, like this, greater or equal to 4, there are two series of examples. There are two examples, which I'll now describe. I'll just do an example. So let me take a product of a K3 with itself, and let me consider the quotient of this by the symmetric group. So as before, this is a singular variety. It's singular along the diagonal. And in fact, the singularity here is just the singularity that I wrote there. That is just that it's not isolated, but it's locally a product of this singularity. So for the same reason that that thing had a symplectic resolution, then I have here something that I'll denote S square bracket 2, which is holomorphic symplectic. And in fact, it is irreducible holomorphic symplectic. So this is one of the two examples. And there's a similar example where instead of starting with a K3, I consider a 2 torus. And then, so this has C1 equals to 0, and then one of the building, I can apply the decomposition theorem. So it breaks into factors. One factor is T itself, and the other factor is this thing called Kn of T, which is a generalized Kummer.
What did you do? What did you take the torus and do what?
Okay, so let me say a more explicit way of defining this. So this essentially is just n plus 1 suppose of points.
What?
So this essentially is just parameterizes n plus 1 points on the torus.
Unordered.
Unordered, yes,
Is this
thank
a
you.
symmetric product? I missed that.
This is a resolution of the symmetric product.
It's after the symmetric product.
Yeah, so it's the same thing I was doing here. So this I should have
Oh,
said.
generalizing that.
Yeah, I'm generalizing this.
Okay, I got it.
So then this has an actual summation map addition. So I have these points on the torus. The torus is a group, I can add them up. And I can take a fiber. This map is isotrivial, so all the fibers are the same. And this turns out to be an irreducible holomorphic symplectic manifold that is not deformation of these two examples, of dimension 2n.
But the torus, which torus is it?
So this is
A complex torus to start off with.
of dimension 2.
Oh,
Yeah. And this is called generalized Kummer because in some sense it generalizes this construction in a way that maybe now I won't say. Okay, so in any dimension 2n, I have this example and its deformations, and this example and its deformations. In addition to this, there are two sporadic examples.
but what was S in that example?
This was a K3, thank you. S, K3. So throughout the talk,
No, you said any dimension in this example. So what-
yeah, right, because in any dimension 2n, I can take, instead of 2 copies of a K3, you can take n copies of a K3.
Okay.
The only advantage of dimension 2 is that you could have just said blow up the diagonal before you divide it up. and that would be- That would be the resolution.
Yeah,
More complicated.
absolutely, absolutely. Well, on a dense open subset, it's just this thing, it's the same. This cone times a smooth locus, but then of course, when there are more points colliding, the singularity becomes worse.
So,
Yeah.
well, I don't, the kind of two kind of examples. One is Roman and Bob, but I didn't, they seem to be the same thing. I mean,
Well, except that they have different Betty numbers.
Huh?
So if you consider...
No, I mean, what are the construction vaguely? Just repeat again what the two constructions are.
Okay, I'm doing this for n equals to 2.
Oh, I want for N.
Okay, well, I can take the product of S with itself, n times.
Okay.
Then I can take the quotient,
Okay.
I'll call it like this, the quotient by the symmetric
And S is K3?
on n elements, SK3. Throughout the talk, S is a K3.
And then what's the other one?
And this is the same thing. So let me finish so that just to introduce the notation.
Involved, yeah.
And I have this n here. So square bracket n will be the resolution of this symmetric product. I do the same thing. Instead of starting with a K3, I start with a 2 torus.
Oh,
Okay? But it's not irreducible in the sense that I defined earlier. And I have two ways of seeing this. Either I just apply the theorem and look at what are the factors. Up to a finite cover, it breaks into a factor. And the factors are this guy and this guy. A more geometric way of saying it is I have the addition map and I take the fiber.
K3 itself was the product of two, was the...
This
Divide
construction would give you K3 if you did it for n equals 1.
One.
I mean,
Yes. Thank you.
I mean, but
Yeah.
all of these, both of these examples were made out of a flat torus and doing things
Yeah.
with finite
Mhm.
groups and
Yeah,
resolving
yeah,
and so on.
yeah. Absolutely.
That's
That's what I was trying to show, that you have very naturally singular things, and by resolving these singular things, you get these smooth guys.
You move from the left.
Right,
Flat thing
yes,
over
for
there.
example, yeah. But in fact, so I said that these are the examples, but then there are also deformation of these examples, which of course won't be of this type. But in fact, you can take moduli space of vector bundles on the K3. This is something I was planning to say later, but let me just say it now.
Complex and electric like an open condition when you deform it.
Yes,
By the way,
thank you. So
why
deformation.
is this being attributed to Bogomolov? Because his main theorem was that these don't exist, right? He had a false paper.
Yes, I know,
Which-
but actually, so I know the paper of Baville. I know the paper of Baville, and
Bogomolov was
it-
just very nice.
yeah, okay, yeah,
Well, they almost don't exist.
almost. That's right.
Right, I mean,
Well,
they're a very surprising theorem, right? You just put this condition, and
Mhm.
it's just very rigid set of things.
Absolutely,
It's amazing.
absolutely.
They almost don't exist.
Yeah, and sometimes they shouldn't exist,
Huh?
and sometimes maybe
They
they
almost
shouldn't
don't
exist.
either, apparently.
But in fact, so
The key point is the holomorphic form on a Colloquium has to be parallel, and then you just apply the shape.
yeah, the
Well, all these theorems, yeah, right.
yeah. All right. So then what I wanted to say is that there are two sporadic examples. So two sporadic examples of dimension 6 and dimension 10 due to O'Grady. So I want to describe them now, I'll describe them later, if there's time. So the point is that, as it's been noted extensively, these are not many examples of these things, and in fact, we have no idea if the examples that we have are all, or if there are others. For example, there's these two sporadic things that don't appear in the other dimensions, where in the other cases, you have one, apart from the dimension 2, you have one in each dimension. And people have no idea if these are just two elements of a series, or in fact, they're just two things. I mean, there are wild speculations about this. But the main problems in the field are to classify, construct new example, or to give different geometric descriptions. So new geometric description. So what I mean by new geometric description, I said that, so if I take one of these guys and I deform them, it stays holomorphic symplectic, but it will not be construction of this type. And people are trying to describe some of these deformation, some of these elements of these deformation classes that are not represented in this form. So before I go ahead, I just wanted to say that there are so yes, there are a few examples, but in fact, there's this very rigid geometry, which I would like. One of the aims of this talk is to try to express this rigidity, but it also allows to actually do many computations. So in fact, there are a lot of conjectures in algebraic geometry. They are completely inaccessible for a general variety. But in fact, their incarnations in this case are actually more approachable. So they're more approachable. So for example, they're sort of important conjectures that relate the space of algebraic cycles on an algebraic variety, and I don't think I want to get into details because the time is running fast, but I just want to say that these irreducible holomorphic symplectic manifolds are a testing ground for many conjectures.
So you're talking about these like they're algebraic varieties, but actually most of these are not.
Most of these are not. You're right. So in the deformation space, there's countable unions of codimension 1 loci that are algebraic. But in fact, the general one will have no line bundles at all. So yes. And in fact, one of the richness of the theorem is that this interplay between the non-projected case and the projected cases. So many results that you prove for projected varieties actually pass by the non-projected case. So for example, there's a theorem of Huybrecht's that shows that if two irreducible holomorphic symplectic varieties are birational, then they're deformation equivalent. And this uses the fact that the general Hyperkähler manifold, irreducible or symplectic, has pick equal to 0. And so this is just one example, but I could do many examples. So there is this, one of the richness of the thing is that you have this freedom. And in fact, earlier I mentioned the twistor lines, and the twistor lines are greatly non-algebraic, but in fact you ended up proving results on algebraic manifolds using these twistor lines. Okay. So, what I wanted to talk about now is a structure theorem for maps from them. So structure theorem. And I'm going to add with connected fibers. For maps from irreducible holomorphic symplectic manifolds. And let me start with the example of the K3. So this structure theorem, as I will say in a second, says that essentially there are only two types of examples: symplectic resolutions and Lagrangian fibrations. So Lagrangian fibrations I'll define in a second, but they're sort of the analog of the interval systems in classical mechanics. And for K3 surfaces, this
maps from,
yeah.
to anything?
Yes, but in fact, one of the points is exactly there are only two possible targets essentially. And for a K3 surface, this is a pretty natural thing. So for a K3 surface S, we saw that it can map to a singular K3. Okay? So I want to exclude quotients by finite groups. That's why I put connected fibers. So then the other maps.
Holomorphic maps?
Yeah. So yeah, for memorphisms.
I think that's the reason that.
Oh, I see. Okay. I see. Yeah. Thank you. Okay, so we have a map from a surface to a surface, which is biholomorphic on an open subset. The other map, I can map a surface to a curve. If I map a K3 to a curve, the curve has to be P1. Not only this, the general fiber will be an elliptic curve. An elliptic curve that is Lagrangian with respect to the holomorphic form. Okay, so yes, it is. These are called elliptic K3 surfaces. In some sense, it is surprising, but from a K3 surface, you can either map to a surface. You don't care about mapping to a point, of course. So either to a surface or to a curve. And then you can believe that you have a structure theorem for this. But for higher dimensional irreducible holomorphic symplectic manifolds, the same dichotomy holds. So let me say what the theorem is. So first, let me recall the theorem of Matsushita. So X. Okay, I don't speak Japanese. Irreducible holomorphic symplectic, and F from X to Y, a proper morphism with connected fibers. Then there's an alternative. So either F is a symplectic resolution. So it's just the same thing as we had earlier. So Y is a singular symplectic manifold, and they're biholomorphic away from the singularities of Y, and the symplectic form in Y extends to a symplectic form on the whole of X, which are generalizations of the examples that I did earlier. This example and that example. And I should say that, in fact, okay, I'll say that later. And the second thing is that the dimension of Y is equal to n. So if this is a IHS, the dimension 2n. So it's half dimension. And the general fiber is a Lagrangian torus. So this is what is called either Lagrangian fibration or algebraic completely integrable system.
So it's Lagrangian with respect to the complex symplectic form.
Lagrangian, thank you, with respect to the holomorphic form. The holomorphic symplectic form. Yeah.
Well, these two cases.
Yeah. Sorry?
These
Yeah,
two cases.
exactly. But of course, you know, for a surface, you can't, you know, there's only those dimensions, but this is the amazing thing. And the other thing is that if Y is smooth implies Y equal to Pn. And it's conjecture that it's always smooth.
Oh, yeah.
So examples of symplectic resolution in the non-compact case arise in representation theory. So Springer resolution is an example. There are many quiver varieties that have a symplectic structure and a symplectic resolution. And for this kind of maps, other examples that come in representation theory, for example, the Hitchin system, the moduli space of Higgs bundles.
So I can imagine non-compact things make good sense in algebraic geometry, but how do you make sense of it? I mean, how do you deal with it? Is there something you have to say about non-compactness? Do we just do complex manifolds?
For example, you need to ask the form to be closed, which I didn't ask earlier. Yeah. Is that what kind of thing are you asking?
I don't know. It could be wild somehow. I don't know.
So the non-compact examples that I'm actually referring to are all algebraic. Okay. So they're all like, for example, the singular ones are affine, and and then
compactification.
They don't. All the examples that come from representation theory don't admit a homomorphic symplectic compactification.
Oh, homomorphic symplectic.
Yeah.
They admit compactification.
Oh yes, or like for example, quasi-projective. So yeah, you can just close them up and project.
Yeah, if you don't ask for anything like that, they can be just completely crazy, even if they're topologically extremely simple.
And so something that I should say is that not every singular symplectic manifold has a symplectic resolution, which is in some sense what you're saying now. Like you have a holomorphic symplectic manifold, you say quasi-projective or fine, and you close it up, you add some singularities on the boundary, but then you try to resolve them, and generally speaking, the resolution won't have a symplectic form. So it's a highly non-trivial thing to understand when something has a symplectic resolution, or even when it doesn't.
So which cotangent bundle of projective varieties have a symplectic resolution?
The cotangent bundle is smooth.
No, have a symplectic resolution of their compactification.
Oh, I don't think any, because there are too many holomorphic forms. Rational curves. The fibers are vector spaces, and so so you can control what the deformation space for rational curves on a Hyperkähler manifold, and for this reason they can. But
where are the curves you're getting? Oh, all the lines, all the various lines and planes.
Yeah.
Okay.
So, but the important thing, and this is something I was going to come up later, is that these singular things are the local model for many symplectic resolution in more general, in the compact case. So one sort of simple topological consequence of having a holomorphic symplectic structure is that all of the every other Chern class has to vanish, right? So all of the odd Yes.
Chern classes vanish, so you would definitely see there are huge topological
Oh, yeah,
abstractions.
thank you, you're right, yeah, I should have said that, yeah.
It's because the holomorphic tangent bundle is isomorphic to its,
To its dual.
dual, just by contracting with the
Yeah.
symplectic.
So any symplectic vector space is isomorphic to its dual, and if the form is symplectic, you have a holomorphic isomorphism between the tangent and cotangent bundle.
So these things are so wonderful, they almost don't exist.
Right, yeah.
But they do exist, so you can give a talk.
Yeah.
That's a good geometry.
So I'm running a little out of time. So let me, because I brought up this thing up, and Dennis was suggesting these things about compactifying, and so what I said earlier was that these symplectic resolutions that come from representation theory are often the local model for these things. And this is a theory that I want to
They
say.
have symplectic compactifications, right? The ones that come from
Well, so
the-
by local model, I mean local analytic, so in the Euclidean topology. So it's not that if the local model is an affine variety, it doesn't mean that the whole affine variety has a symplectic resolution. So okay, I'm kind of behind in. So one source of symplectic resolutions in the compact setting is moduli spaces of vector bundles. On, say, a K3 surface. I should say, by the way, the two sporadic examples in dimensions 6 and 10 were found by a symplectic resolution of singular moduli spaces. So that's something I was planning to talk about, but I don't have time. Anyways, so if I fix a topological type, for vector bundles, so V just means I'm fixing the Chern classes of vector bundles. I want to parameterize vector bundles. So I can consider the moduli space of vector bundles on S for these Chern classes. And in fact, it turns out that this is an algebraic variety. So this is one of the features of algebraic geometry. That parameter spaces are itself algebraic varieties. And in fact,
S
is always a K3. Sorry?
Always K3.
Always a K3. Yeah. And so it's a theorem of Mukai that these moduli spaces are irreducible holomorphic symplectic, and they're deformation equivalent to the examples that I described earlier. Okay. So this is another very interesting thing, is that the higher dimensional analogs of these K3s are vector bundles, moduli space of vector bundles on a K3 surface.
When smooth.
When smooth, thank you. So when smooth, okay, so there's a very particular class of symplectic resolutions that arise in this context, which I don't really have time to describe, but I'll just say a few words. So when you consider moduli space of vector bundles, it's not enough to fix a topological type, because you also want to choose a stability, because if not, the vector bundles are too many. So H will be my stability parameter. If I choose the Chern classes in a good way, and if the stability parameter is general, then this is smooth. So it's IHS.
Lurch with the stability parameter.
Sorry?
The left is in the lurch with the stability.
You want to know what it is? Or
Yeah, well, I mean, I don't want to know, because like running out of time.
She gets to be
Okay.
more
So
specialized.
back to
Okay.
yeah. It's a choice of an ample class if you want. Tells you which stable vector bundles you're considering.
Oh.
Okay,
Good.
but if for general thing, it's smooth. But if you degenerate H to something which is not general, you have a map to NVH0, and now this is singular. Okay? So this is a very natural class of symplectic resolutions that arise in this context. And I didn't have time to motivate the reason why you care about these things, but in maybe I'll say something later, but it's, first of all, they're very natural because you don't want to just fix one stability condition. You want to, like, because it's a choice, so you don't really want to make a choice, so you look at all the possible choices at the same time. And also, there's this thing called wall crossing, which relates different moduli spaces with respect to different parameters when they're smooth. But anyway, so let me just say that there's this class of symplectic resolutions. So, so the theorem that I want to mention is joint with Barello. Is that, so here so if I have this map like this, so these are conditions on V. So I didn't really have time to say what the natural conditions. So with some natural conditions, on V, the resolutions as above are modeled by quiver varieties.
So you're saying that this degeneration that you did is one of these two classes of maps?
Exactly. So yeah, the reason why I did the structure theorem is that, yeah, thank you. These are essentially, because they're the only maps and the only way you can actually put your hands on these things. And if you want to construct them, you want to either use one or the other. And so of course you need to understand if you want to use the symplectic resolutions. So my idea was to mention a result in this category and this category. So the result in that category is this theorem with indigo. So the point is that these moduli spaces can be very complicated. But the content of the theorem is that you have these varieties that come naturally in representation theory that constitute the local models of these things.
These are like graphs with vector
Yeah,
spaces and
exactly,
maps between them.
exactly, yeah. I don't have time to like say more.
There's a
more
linear
about these,
algebra
but-
idea.
Exactly. So the point is precisely this: that you're reducing a problem, some vector bundles or sheaves, to a problem which is linear algebra. It's very hard linear algebra and hard combinatorics.
Right.
Not saying that, but still, it's things that people have studied a lot more. And in fact, there's a central condition here, and the reason is that we consider Giesecke stability, and the right context for this is bridge instability. So our theorem is only for the Giesecke stability, which is the more classical theorem. So now I'm working on with McCree on generalizing this thing. In fact, I mean, there are other people also. So yesterday, the seminar yesterday was sort of a partial generalization of this theorem or a definition for this theorem. But what I'm saying is that because the representation theory side has been studied so much, the hope is that you can use some of the information there to translate back. And for example, there's a particular case of a conjecture of Kawamata that relates to different symplectic resolutions. And so there are things that have been said on the quiver variety side, and so the hope is to transfer this information. And the point is that this is like really a dictionary, which is really explicit. It's something that you can really sort of, like how you get the quiver is something that, given the point, a singular point, like I can tell you what the thing is and what the resolution is, depending on what this thing, what the stability of the parameter is.
So in these cases, you can actually construct the thing explicitly in Hyperkähler quotient. Is that?
Yes. So yeah, exactly. So the quiver varieties are symplectic because they're obtained by symplectic reduction. So there's the quiver representation, the symplectic vector space. You consider the moment map. You take the quotient, so you get a symplectic a structure on the smooth locus of this quotient. Yes.
But Mukai's theorem doesn't involve that kind of idea at all?
No, not at all. No, because this is the quad. So the moduli space are cushions of the Cot scheme, which has nothing to do with any symplectic anything. So the symplectic structure here only exists on the quotient. It doesn't exist on the thing upstairs. Yeah.
Does this smooth this condition actually tell you that H2 of the trace-free endomorphism?
Yeah,
it's
the
actually
smooth
zero?
Exactly.
So in fact, it's unobstructed.
Exactly. Yeah. because on the K3, x2 is dual to Hom, and so if the thing is stable, then there's no Homs, no Homs except the scalars. But yeah, okay. So let me mention the other thing in the other theorem in the context of Lagrangian vibrations. So I was planning to give a longer introduction to this thing of Lagrangian vibrations, but I'll just, I guess, just state the theorem, and then I can happy to talk about it for as long as the time allows. Okay, so whatever I said so far is, roughly speaking, you have these K3 surfaces, and then you do some construction from K3 surfaces, and you get, or from a torus, and then you get these higher dimensional things. What I'm going to talk about next is something where instead of starting from a K3, you start from a cubic fourfold, which is something that is apparently completely unrelated. It's a Fano variety. It's of dimension 4. It has no holomorphic forms of any degree, let alone a symplectic form. But there's something that was in fact first pointed out by Deline and Rappaport, that there's something about the Hodge structure of a cubic fourfold that is very similar to the Hodge structure of a K3 surface. And in fact, this allows, this implies, in a way that I don't have time to say, that you expect that many geometric constructions, starting from a cubic fourfold, actually carry a holomorphic symplectic form. So the theorem I want to talk about is a specific case of this. So let X be a cubic fourfold. So it's locus, the zero locus of a homogeneous polynomial of degree 3 in P5. And so if I choose a hyperplane section, a hyperplane of this P5, and I intersect it with X, this is a cubic threefold. No, this is this. Oh, sorry. Yes, thank you. Okay. So attached to a cubic threefold, Simonson Griffiths associated something called the intermediate Jacobian of Y, which is a complex torus, in fact, in abelian varieties, of dimension 5. It's a very sophisticated invariant. In fact, it tells you precisely that cubic threefolds are not rational. Okay, so we have a P5. We have an abelian variety of dimension 5. What you want to do is you want to move it and create a Lagrangian vibration. So in fact, what Donati and Markman do so if I let U, so I consider the P5 dual parameters the hyperplanes, and for any point here, I have a cubic threefold that is smooth, and I can consider the intermediate Jacobian. So I have the families of abelian fivefolds. And the theorem of Donati and Markman is that there exists a holomorphic symplectic form on this JU.
What's U?
So U is an open subset of the hyperplanes in P5, parameterizing hyperplanes whose intersection with X is smooth.
So on JU, you mean the full JU or on one of the fibers of JU?
No, so it's the fiber is in abelian fivefold, so it can have a symplectic form on the total space of the family.
Oh.
Sorry, and I should say, with respect to which this map is a Lagrangian vibration.
So the writing's a little messy, but that's first J is a J sub Y.
Oh, sorry, yes.
The other one is a J sub U. That's all the
Sorry.
JYs for Y.
Let me write J of Y, the intermediate Jacobian, and then as I vary it, sorry, yes.
Some of the fibers have this.
So now they're all smooth.
What's the statement?
That there exists a holomorphic symplectic form on this quasi-projective variety. And with respect to which, the vibration in abelian fivefolds.
That's JU or JY there?
This is JU.
No, you just said it's 5-dimensional.
That's the fiber.
No.
The fiber is 5 dimensional.
Fiber is
Sorry.
5 dimensional.
It's a 10-dimensional complex.
It's a 10-dimensional complex, yeah, quasi-projective variety. So I have this thing,
I
JU.
think it's 10-dimensional, there's a 4
Right,
plus
right,
5.
right. JU equals the set of all J of Y. What of Y?
The J of Y.
Y equals H
X
intersection H. H is in U.
Thank you.
Hyperconnection for that.
Generic.
Does that make sense?
And Y smooth. Or J of Y.
Well, the U here is that it's
I
smooth.
can do that part.
Okay, so the theorem with Radu and Voisin is that there exists an IHS compactification J of this JU. So IHS, a smooth IHS projected compactification. Together with a map, pi, from J to P5, which extends that map. And in fact, this solves a conjecture. This was a conjecture.
Is this different from the O'Grady example?
I'm going to say that, oh, right. And moreover, this is deformation equivalent to O'Grady 10. Okay. So this is a conjecture of Benagi-Markman from 94, the part that the existence of a symplectic resolution, and then Markushevich and Tikhomirov and Markushevich Kuznetsov, the part about O'Grady 10. So I guess my time is over. Let me just comment that
So
J is 8-dimensional. Huh?
10.
Huh?
10.
Well, the 3
Tori
plus
is
5.
5? The fibers are 5 and the base is 5.
What's 5? What's
5
over
is P5.
No. What's the fiber? What's the
The
fiber?
fiber is the, so let me start here. This is a space that parameterizes hyperplane sections of this P5. For any point,
Oh,
I can consider the intersection of X and I get a cubic threefold. You parameterize the hyperplanes whose intersection is smooth.
yeah.
Okay? For any such thing, I have an intermediate Jacobian, which is dimension 5. And so the fiber of this map are such
Oh,
objects.
you took the Jacobian on me. Okay, I didn't hear that.
Yeah,
But J-
this was,
J
Yeah.
means,
yeah.
oh, J of Y,
Mm-hmm.
which is 3-dimensional.
Yeah.
5.
5.
No, Y is 3.
Y is 3, yeah, Y is 3, Y is 3, that's right.
J of Y, J of 3 is 5.
Yeah, exactly.
Oh, I got 8.
So let me just comment that, first of all, the method to compactify is by using prim varieties. And in fact, this is the first example of Lagrangian vibration that is not a Jacobian of curves, in principally polarized abelian varieties that are not Jacobian of curves. And in fact, if you take a look, one other thing I wanted to do is vibration intermediate Jacobians, and those are in the examples K3n, the previous example. So people are trying to construct these prim varieties, the vibration in prim varieties, or in general, things are not Jacobian of curves, but in fact, people were not, I mean, this is the first example where this has been achieved. And the other thing that I wanted to mention is that this is a more general construction than the one given by O'Grady. And in fact, so for example, we don't even know the Betty numbers of the O'Grady 10. The O'Grady 6 was calculated recently in a joint work with Mongardi and Rapagnetta, but the O'Grady 10 is still pretty unknown. But in fact, using this thing, we might be able to actually understand this example more.
So
And
does pi have singular fibers?
yes, of course. For topological reason, they have to have singular fibers. So, I mean, the challenge here is exactly this, that you have to understand what singular fibers to add. So the singular fibers to add are singular prime varieties. So there's the general construction of Clements and Griffiths relates the intermediate Jacobian to a prime variety. And Casalina, Martin, and Gruszewski, Hulick, and Laza had sort of generalized these, this sort of Clements-Griffiths construction and looked at singular prime varieties. And so, using some ideas that appeared in a paper with Albarello and Ferretti, and also came from my thesis, what we do is we find a smoothness criterion for these family of, we define our relative compactified prim. There exists relative compactified Jacobian. And so the point of this is that we have this definition which goes beyond this example of a relative compactified prim, and we prove a smoothness criterion for it, which is satisfied, I should have said, for general X. So for general X. I should say that in a forthcoming paper with Radu, Claire, and Kolar, we're giving a different proof of this that involves taking limits of hyperkähler manifolds. That was just
So X here is the cubic. So
X is still a cubic, yeah. And okay, over time, let me just say that there's this connection between cubic fourfolds and hyperkähler manifolds and K3 surface that is something that is still mysterious. And this is one example of a connection. There are others, which I was planning to talk about, but I didn't have time. But in fact, so it's known that the cubic fourfolds, it's known that cubic threefolds are not rational by work of Clements and Griffiths. No one has any idea about the rationality or not of the cubic fourfolds. The only conjectures that are around are in terms of some hyperkähler manifolds that are associated to a cubic fourfold. So this is one of the reasons why a lot of people have been studying these hyperkähler manifolds that come from cubic fourfolds. Okay, thank you.
Any other questions?
Is there a simple idea to explain how you would go about trying to prove that one of these is deformation equivalent?
Yeah. Well, there's something I wanted to talk about, and I didn't have time. So the moduli space of cubic fourfold is 20-dimensional. In this moduli space, there are countable unions of divisors, where these cubic fourfolds have a very special Hodge structure. And this special Hodge structure is very intrinsically related to a Hodge structure of a K3. And it's not really, this is a purely Hodge theoretic statement. On the other hand, for some of these divisors, this relation, which is only Hodge theoretic, is actually geometric. So to a cubic fourfold, you can like, if you have a cubic fourfold in one of these categories, I can give you a K3 surface. And so for example, if a cubic fourfold contains two planes, you can project from one plane, some kind of geometric construction like this. I can tell you later if you want. And the point is that you specialize your construction to one of these special cubic fourfolds. And then somehow you relate this intermediate Jacobian vibration to a moduli space of vector bundles on this K3. It's not a simple construction. In fact, this is why we're reproving this statement with Radu, Claire, and Kolar. Because if you degenerate to a special cubic fourfold, but not too special, the construction is very hard. If you specialize to a very singular cubic fourfold, this relation is much simpler. But then you have to deal with these singularities. And so this is why I said that we studied limits of hyperkähler manifolds. And it's sort of a generalization of the Kulikov limit of K3 kind of classification, so to say.
So I'm just wondering if it could be meaningful to consider Hamiltonian holomorphic laws on holomorphic symplectic manifolds. Anybody consider this such objects?
So
Hamiltonians would be constant, right?
So
No, but on open subset, you
well, you
probably
can
mean,
consider
right?
meromorphic Hamiltonians are local.
Yeah, so I don't think anybody has considered it. So, of course, on these maps to P5, you can give locally maps to P5 or PNs, and those would be Hamiltonian functions. But yes, I don't think people have studied the flow associated to that.
I guess if you
have on a
pull back a function from a meromorphic function from the P5, it's going to be one of the invariants.
Yeah.
The rest of the P5s will give you the rest, and you do this action angle game.
I mean, in the
And
non-
study the flows, they'll just move things
But they'll
around.
move it on the fibers.
But that's always
Yeah.
what happens in these
Yeah.
completely integral cases.
So
But I mean, there's a certain sense when there's an old story that in looking at these holomorphic flows locally. So when you have a twistor vibration, you can use Darboux. You have Darboux charts,
Yes.
right? And then to get from one Darboux chart to another, you have a holomorphic symplectic morphism. So now, as you change from one, as you now change from one twistor fiber to another, you have a change of the transition function.
Uh-huh.
Right? And so, in a natural way, you do get there's a whole holomorphic section of the pullback of the O2 line bundle that actually arises as the Hamiltonians. And these deformations are associated with elements of homology coming. So there certainly is there's locally a completely sensible use of Hamiltonians of vector fields and so forth, but in terms of global structure, I'm not sure much.
No, I don't think that on the global structure, but even locally, I mean, what would be an interesting question about these things? That's what I'm wondering.
Locally, probably nothing interesting is going on, right? So you should allow some singularities for these positions. You should
So one thing is that that like I just thought about as you were saying this is that as we pointed out, some of the fibers are singular, and in fact you can kind of using these maybe exactly what you're saying actually you can actually understand what the singular fibers look like. For example, so the general fiber is a complex torus. The singular fibers will be a complex torus of dimension 1 less times, so when you have a lattice that degenerates, right, you get a C star. And so using these sort of maybe, it's probably, I think the techniques to prove this kind of statement about singular fibers, I think is something like what you're referring to.
Well, for instance, could you give an example when there is a leaf of this foundation which is dense in the manifold? So,
No, I think they're always algebraic, the leaves.
so they're always algebraic. There is
In these cases where you have the compactification.
I mean, I guess one way to think about it, if it's global enough, then what she said is there's a structure theorem of maps. So
Yeah.
you can't have just arbitrary Hamiltonians.
So what are assumptions on these maps? They're proper assumptions?
Proper.
And
Proper.
connected fibers.
So
Proper.
if you consider meromorphic maps, not proper maps.
No, I'm sure if you sort of remove the strict globality, you should definitely be able to do something. It's not, maybe it falls into another category.
Yeah, I guess, yeah.
Okay, let's try and speak